Good morning, kids. Today we're going to do actually my last lecture I'll be doing for you before I return. Today I'm going to talk about the mean value theorem very briefly, and then I'm going to give you some notes on doing some more complete graphs, sketches that include points of inflection and vertical and horizontal asymptotes. So I'm going to start with the homework. The homework that you will need to do, I'm going to the end of everything here. The homework that will be due this coming Thursday, the 19th, will be a worksheet on graphing with inflection points. And you'll do all of that, and that will be due Thursday. The worksheet looks like this. It should be in the Calc 1 drawer. There are 5 problems, and Ms. Haney will pass that out to you. What you need to do with number 3 here, it was a typo. So when you do this, just subtract these before you start. So on the worksheet, you should start out by subtracting and simplifying this function. It actually turns out to be a parabola, so it should be pretty simple to do. This is f of x equals negative, let's see here, 7/4 x squared. So that's just a simple parabola that you need to graph when you do the worksheet. Please pick up on that. Don't make it more complicated than it is. And then the other 4 problems on your homework are pretty complicated, so you'll need to allow ample time for those. That's the worksheet, and that is due on Thursday. Then on Thursday, there will be no lecture. There will be just work time, and the homework that will be, and of course Ms. Haney can go over the worksheet too. The homework that will be due on the 23rd, Monday, the day that I come back, will be page 187, numbers 1 and 3, page 192 to 193, 1, 3, 9 through 19, odd, and 201 to 202, 1, 3, and 9 through 19, odd, and 63. That's homework that will be due on Monday. It will be assigned on Thursday. There's no lecture for Thursday. So, without further ado, I'm going to now get to the lecture for today, which is pretty lengthy. If you don't finish the lecture in class, you can watch the rest of it on the video at home. Today we're going to talk about the mean value theorem. I want to make sure my video is going before I start here. Yep, it's going. All right. So the mean value theorem, very briefly, I'm going to talk about what the mean value theorem says basically in words is if you have an interval and a graph between 2 x values in an interval, and you take the slope between those 2 x values, a and b, in an interval, then what you will get is a slope that has to occur somewhere between those x values in the interval. So, for example, if you get a slope of f of b minus f of a over b minus a, which is the slope formula, between a and b, then that slope must be the derivative at some point between a and b. Okay, so there has to exist some value x equals c between points a and b where that slope is the same as it is between a and b. That is the mean value theorem. Now, algebraically, it looks like this, and you just set up a formula, and you basically normally have to find that c. All right, so I'm going to do an example with you. Find the value or values of c that satisfy the equation, the mean value theorem, f of b minus f of a over b minus a equals f prime of c, for the function f of x equals tan inverse of x on the interval from negative 1 to 1. So first we have to find the slope between negative 1 and 1. So to find the slope, we have to find the 2 points. Okay, so this is x equals negative 1, so I'm going to take f of negative 1 equals the tan inverse of -1, which I know you all must have memorized. That is negative pi over 4. And then f of 1 is equal to the tan inverse of 1, the angle whose tangent is 1, and that is pi over 4. So the slope between f of -1 and f of 1 would be equal to the following. Pi over 4 f of 1 minus, well, I should actually write the formula down so you're not confused. F of 1 minus f of -1 over 1 minus -1. So the bottom turns out to be 1 plus 1, or 2, and the top turns out to be pi over 4, that's f of 1, minus negative pi over 4. Well, that's pi over 4 plus pi over 4, which is actually equal to 2 pi over 4, or pi over 2. So what you end up with is pi over 2 over 2. And if you take pi over 2 and divide it by 2, it's like multiplying it by a half, so you get pi over 4. So your slope between the 2 points is pi over 4. So there must be some derivative of this tan function, tan inverse of x, between -1 and 1 that is equal to pi over 4. So what you're going to do is you're going to say there's some value c where f prime of c is equal to pi over 4. And you're trying to find what c is, what that x value is, where the derivative is pi over 4. I'm going to slide that over just a little bit, put up a little fence here so they don't run in together. First thing we got to do is we got to take f prime of x. Okay, so if f of x is tan inverse of x, then f prime of x is equal to 1 over 1 plus x squared. Right, so f prime of c, if we were to plug in c, f prime of c is equal to 1 over 1 plus c squared. So now let's put that over here into our equation. So 1 over 1 plus c squared is equal to pi over 4. And then you just solve this. You cross multiply and you get pi plus pi c squared is equal to 4. Pi c squared is equal to 4 minus pi, and then divide both sides by pi, and you get c squared is equal to 4 over pi minus 1. And then you just take the radical of both sides, and you get c is equal to plus or minus radical 4 over pi minus 1. And that is the solution to the mean value theorem. The mean value theorem is a very important theorem geometrically, and you need to be able to apply it. So you need to be able to do what I just did. It's very simple. You set the slope between the 2 points equal to the slope at a point, and then you just solve for that value, whatever c needs to be. That's the only example I'm going to do of the mean value theorem, and I don't believe there are any mean value theorem problems on your homework tonight. There will be on Thursday's homework, so that's the notes for that. Now I'm going to move on to the meat of today's lesson, which is graphing with points of inflection. Now, an inflection point is a point where the graph of a function changes from concave up to concave down, or from concave down to concave up. Inflection points occur when the second derivative is equal to 0 and when it changes signs. Okay, so the second derivative being equal to 0 is not enough. The second derivative has to change signs. All right, that happens when f prime of x has a maximum or a minimum, because that'll be when the slope of the slope changes signs. Okay, so some things you should recall. f of x has a vertical asymptote at any x value that makes the denominator of the function equal to 0. So we're going to include vertical asymptotes into these graphs today. F of x has a horizontal asymptote at any y value that it approaches as x approaches positive or negative infinity. And then finally, to find the y-intercept of a function, you plug in 0 for x and find y. So we're going to include all of this information on our graphs. We're going to include what we included with the critical points on the graphs, and we're going to include inflection points. So we're going to get a really good picture, a really good sketch of our graphs. So before moving on to inflection points, I just want to give you a good solid review of vertical and horizontal asymptotes. To find the vertical asymptotes of a function, it's very simple. You may have to pause this because I'm going to talk through it very quickly, and then you should pause the video, write down the notes, and then start the video again, and so on, okay? So vertical asymptotes, you set the denominator equal to 0 and solve for x. And the vertical asymptote is a vertical dotted line that is x equals some number. Right? It's always in the form x equals some number. So you're going to include those. Remember, your graph always gets closer and closer to a vertical asymptote as it approaches either positive or negative infinity. And then horizontal asymptotes are the values that your graph approaches as x approaches positive or negative infinity. Okay? So they are horizontal dotted lines. To find these horizontal asymptotes, this is a really simple thing that you should recall. To find horizontal asymptotes, here's what we do. If the dominant number is, or if the dominant power in the numerator, this num stands for numerator, is bigger than the dominant power in the denominator, then there's no horizontal asymptote. So any function that's not a fraction has no horizontal asymptotes. If you don't have a rational function, there are no horizontal asymptotes. So any polynomial, no horizontal asymptotes. So you don't even have to worry about it for the first 1, 2, 3, 4 problems. The first 4 problems on your worksheet will not have horizontal asymptotes. I repeat, the first 4 problems on your worksheet will not have horizontal asymptotes. If the dominant power in the numerator is smaller than the dominant power in the denominator, then there's a horizontal asymptote at y equals 0. Okay? So I just want to give you an example of what that would look like. If the dominant power in the numerator is bigger than the dominant power in the denominator, okay, so that would be something like, for example, f of x equals x cubed minus 3x. That would have no horizontal asymptotes because it's not a fraction. Or f of x equals x to the 4th minus x squared minus 1 over 3x cubed minus 2x. Okay, dominant power in the top is bigger, no horizontal asymptotes. That's what those look like. Okay, if the dominant power in the numerator is smaller than the dominant power in the denominator, then there is a horizontal asymptote at y equals 0. What would that look like? Well, just flip those ones upside down that are up there. All right, so for example, if you had 1 over x squared minus 5x, that has a horizontal, f of x equals, of course. That has a horizontal asymptote at y equals 0. Another example, f of x equals, like I said, you could just flip that up there. 3x cubed minus 2x over x to the 4th minus x squared minus 1. That would have a horizontal asymptote at y equals 0. Okay, so that's what those look like. Finally, if the dominant power is in the top and the bottom, remember, dominant power is the highest power of x, right? If the dominant powers in the numerator and denominator are equal, then make a fraction from their coefficients, and the horizontal asymptote, HASM is how I say it, is y equals that fraction. So an example of that, 3x minus 5x squared, this would be f of x equals, of course, I should make that. So your example here would be f of x is equal to 3x minus 5x squared over 2x squared plus 1. And you'd make a fraction from the coefficients of the highest powers of x in the top and the bottom because they're the same. So it would be negative 5 over 2. Y equals negative 5 halves would be the horizontal line that the graph would get close to as y approached, or as x approached infinity. Okay, I want to change this to purple ink because I'm a little OCD here. Okay, so I probably spent enough time on that. That you actually did get time to copy those down, so that's good. If not, pause the video and go back and copy these right now. Alright, I'm going to move on now to a couple of examples. So these are just steps on the next page. First step, find the y-intercept in all vertical and horizontal asymptotes. Second step, find f prime of x and f double prime of x. Third step, set f prime of x equal to 0. Solve for x. Those are the critical numbers. You found those last class. Next step, set f double prime of x equal to 0. Solve for x. These are possible inflection points. Then step 5, check to see if they are positive. F prime and f double prime are positive, negative, between, before, and after each of the critical points or possible inflection points. You'll need to use number lines that are stacked on top of each other. It all stacks on top of each other. The two number lines for f prime of x, f double prime of x, and the graph. And they should all coordinate. Number 6, find the y-coordinate of each point from step 2 and 3 by plugging it into the original equation, f of x. And then finally, sketch the graph using the critical points, the inflection points, and the increasing, decreasing, concave up, concave down information from step 4. Okay, these are relationships between f of x, f prime of x, and f double prime of x that you'll want to use when you do Thursday's homework, because you're going to have some graphs and you're going to have to look at, well, geez, if f of x has a critical point, then that means that f prime of x has a 0. Or if f of x has an inflection point, then that means that f prime of x has a critical point and f double prime of x has a 0. This chart is very handy. Please keep it handy when you're doing your homework on Thursday. I'm going to do 2 examples of graphs for you now. Let me see how I am for time. Okay, I'm deep in time-wise, but that's the way it goes. So the first graphing example I'm going to do is not going to have any horizontal asymptotes, of course, because it is a polynomial, right? 4 of your 5 problems on your homework are polynomials. So this is 2x to the 6 minus 6x to the 4th. Let's go ahead and take a couple derivatives. So f prime of x here would equal 12x to the 5th minus 24x to the 3rd. Leave some space so you can solve that, and then come down here and do f double prime of x is equal to 5 times 12 is 60, x to the 4th minus 72x squared. Now let's set each of those equal to 0 and solve for x. So when I set f prime equal to 0, I'm going to factor out a 12x to the 3rd. That'll give us x equals 0 as one of our critical numbers. And then on the inside, I'm going to end up with x squared minus 2. That's equal to 0. So if I solve for x, setting each of those equal to 0, here I get x equals 0 because I have a factor of x on the outside. Here I get x squared equals 2. Oops. So x equals negative radical 2, and x equals positive radical 2. Then I need to find, I'm going to find the y values for those right now so that I have them for later. 0, 0, if I plug this, I will plug this back into 2x to the 6 minus 6x to the 4th to find the y values. Negative radical 2 and negative 8, and then radical 2 and negative 8. Those are our critical points. What goes on our number line will be our critical numbers, right? So for my f prime number line that I do over here, I am going to have negative radical 2, which is like negative 1.4. That'll help you when you're graphing. Get a decimal value, put it in your calculator, and then I'm going to have 0, and then I'm going to have radical 2, which is like 1.4. So that'll help you when you're graphing. That's your f prime number line. When you do your number line, remember, you look at the most factored form of f prime of x, which is right here, and you look between, before, and after your critical numbers to see if you have positive or negative, right? So pick a number to the left of negative 1.4, say negative 5, plug it in here, you get a negative. Plug it in here, you get negative 5 squared, which is 25 minus 2, you get a positive. A negative times a positive gives you a negative. This, of course, is 0. And then between negative 1.4 and 0, pick negative 1. Remember, these are all open circles because those are all zeros. So here, between negative 1.4 and 0, pick negative 1. I put that in here. I get a negative. If I put a negative 1 into x squared minus 2, I also get a negative. Negative times a negative gives me a positive. Then pick something between 0 and 1.4. Pick 1. If I put a 1 in 12x cubed, I get a positive. If I put a 1 in x squared minus 2, I get 1 minus 2, which is negative. So this is negative. And then finally, pick a number to the right of 1.4, like 10. Put a 10 in here, I get a positive. Put a 10 in here, I get a positive. 2 positives gives me a positive. So that's my f prime number line. All I do now is I do the same thing for f double prime to figure out if I have inflection points. And really, inflection points, you'll know if you have them even after you graph f prime. It's just a matter of when you get those inflection points, labeling them on your graph. So you set f double prime equal to 0 to find the inflection points. And then you're going to factor out what you can factor out. Now here I can factor out a 12x squared, so f double prime of x is equal to 12x squared times x, 5x squared minus 6. Now these get ugly, I'm not going to lie about that. They get really ugly, the little equations, and you're going to get some radicals and stuff, but no big deal, you're equipped with a calculator. So remember, when I was a kid we had to do everything by hand, and we also had to walk uphill to school both ways, blah blah blah. Okay, so this is x equals 0, but we really did have to do everything by hand. And this is 5x squared equals 6, so x squared is equal to 6/5, and then what you end up with from that is x is equal to positive radical 6/5, and x is equal to negative radical 6/5. I'm going to have to put those somewhere else. Let me put them down here. Whoa, what just happened there? There we go. I'm going to put them down here because I don't want them to get in my way. Oh, I hate when it won't let me move stuff. That just makes me angry. Okay, I'll put them down here. Alright, so once we have those, go ahead, find the y-coordinates so you can get that part out of the way and you don't have to do it later. Remember, go back to the original function to find the y-coordinates. So I'm going to go ahead and write those in red. So I get negative radical 6/5, comma, negative 5.2 approximately, and then positive radical 6/5 and negative 5.2 again, strangely. Alright, so those are your possible points of inflection. Again, in order to figure out if they are actual points of inflection, you've got to do the number line. So let's go up to the number line for f double prime. So I have negative radical 6/5. If you type that in your calculator, that's negative 1.1, which, okay, so check it out. This is negative 1.4, so you want to go closer to 0 to get negative 1.1. Or negative radical 6/5, right? So let me write that as both ways. Negative radical 6/5 or negative 1.1. And then over here, I'm going to have positive radical 6/5 or 1.1. All right, and those are the possible inflection points of f double prime. To see what's going on with those, we've got to look at the most factored form of f double prime. So this is the most factored form of f double prime. Stick something in there to the left, so negative 100. If I stick negative 100 in here, this first part is positive, second part's also going to be positive, so two positives gives me a positive here. There's a 0 between negative 1.1 and 1.1. If I stick that in there, I get a 0 on, let's see here. Oh, 0 was an inflection point. Oh, I forgot to include that. Darn it. Possible inflection point at 0 too. Sorry, kids. So put that on your number line. Okay, so between negative 1.1 and 0, pick negative 1. Plug that in here. If I plug a negative 1 in here, this comes out to be positive. If I plug a negative 1 in here, this comes out to be a 5 minus 6, which is a negative. Positive times a negative gives me a negative. If I put a 1 in there, which is between 0 and 1.1, I get a positive on the outside, and I get a negative on the inside again. So positive times a negative, negative again. So notice that 0 is not an inflection point because there is no sign change. All right. And then finally, after 1.1, say 5, stick 5 in here, it's positive, stick 5 in here, it's positive, positive times positive gives you a positive. All right, so your IPs, or inflection points, happen here and here, not at 0. Your critical points from up here, what do? Well, this goes from going down to going up, so that's a minimum. This one goes from going up to going down, so that's a maximum. This one goes from going down to going up, so that's a minimum. So now you have a little puzzle to put together on your graph. And it's really important when you put your graph together to keep in mind those two number lines up there. So this is going to be hard because I'm not going to be able to see everything at once, but I'll do my best. Since there's nothing that really goes above 0 on this graph, I'm going to do it like this. X, Y. So first let's put in our critical points. We got 0, 0, negative 2, or negative 1.4, and negative radical 8. So negative radical 2 is, wow, I just messed that up big time. Negative radical 2 is the same as negative 1.4. So negative 1.4 and negative 8. So let's put that here. And then we have positive 1.4 and negative 8. So you want to put that about the same distance out on the other side. And you know what happens at those spots, right? Because you can see it up here. Here, there's a top. All right, so I'm going to put a top in here. Here, there's a bottom. So I'll put a bottom in there. Oops, that was a horrible bottom. Let's try again. A minimum or a bottom, okay. And here, there's a minimum. So I'll put a minimum in here. I'm using improper math terminology, so I better fix that. Okay, now, once you have those, there's really only one way to connect the dots, right, kids? So then, after you connect the dots, that's when you'll put in your inflection points, okay? Because your inflection points happen at those other points that you have. But if you connect the dots, the inflection points should occur naturally. There is a spot between there that this changes from concave down to concave up, from smiling to frowning, and from frowning to smiling. There are no other inflection points, so we just draw the arrows here going up off the end of the graph. Okay, so your inflection points happen here at radical 6/5 and negative 5.2, and over here. Okay, put them in the same spots. Okay, radical 6/5 and negative 5.2. Now we got to label all our points, and then we're going to be done. So this is 0, 0. This is radical 6/5, comma, negative 5.2. This is negative radical 6/5 and negative 5.2. This one down here is negative radical 2, negative 8. And this one is radical 2, negative 8. So all of those have to be labeled. And then, of course, your graph of f of x has to be labeled. So f of x equals 2x to the 6th minus 6x to the 4th. And there's your graph. Okay, so where are your maxes and mins now? All right, so you've got it all labeled. You have your inflection points. Now we have to label where the maxes and mins are. Well, what you have in your picture, this is a local max at 0, 0. Why is it only local max? Well, because these arrows go up forever, right? So eventually they're going to pass that max. So it's a local max at 0, 0. You have a absolute min. It's the smallest value that you could possibly have. Absolute min at both radical 2 and negative 8 and negative radical 2 and negative 8. Okay, so that's that. Remember, this was a polynomial, so in the beginning I should have stated that there are no vertical or horizontal asymptotes. Okay, and I also should have plugged 0 in for y to find that the y-intercept is equal to 0, which you find out eventually anyways. Alright, so that you should do at the beginning. I got all carried away with the calculus part, forgot to do that part. So that's what your sketch should look like. You need to say what your absolute mins or local maxes and mins are when you're done, and label them on your picture. It doesn't hurt to put them somewhere else as well, and that's that. Now I'm going to go on to the next one. I'm going to try and be quicker, although I don't know if there's any possibility of that happening. So the next one is, I'm going to do on the next page, even though you should too, on a separate page on the back or something, because this is a long problem. So you got f of x is equal to x over x squared plus 1. Let's first of all look at, are there vertical asymptotes? Is there going to be a place where the denominator equals 0? No, because x squared plus 1 will never equal 0. So there are no vertical asymptotes. Are there horizontal asymptotes? Well, yes, there is. Because the power on the top, the highest power of x on the top, is smaller than the highest power of x on the bottom, the horizontal asymptote here is y equals 0. So as you approach infinity and negative infinity, this graph is going to get closer to 0. And then finally, what's the y-intercept? If I put 0 in for x here, the y-intercept of this graph is equal to 0. So that's all important information. Now I'm going to find f prime of x and f double prime of x, and then I'm going to do you a pretty graph. So very quickly I'll find f prime of x. If you need to pause it, pause it. F prime of x is equal to the bottom, x squared plus 1. Remember, we got to do a quotient rule. Times the derivative of the top, 1, minus the top, x, times the derivative of the bottom, 2x, all over the bottom squared, x squared plus 1 squared. Then I'm going to just do the algebra there, and I get f prime of x is equal to x squared minus 2x squared, which is negative x squared, and then plus 1. So 1 minus x squared. If you need Ms. Henny to do another step on the board for you on that, she'll gladly do it, I'm sure. And this is x squared plus 1 squared in the bottom. So that's f prime of x. That's not the hard one. We'll take that, we'll set it equal to 0. So when you set f prime of x equal to 0, the only thing that makes it equal to 0 is the top. So you're just going to set the top equal to 0, and you're going to use the top to determine the critical numbers, because the bottom's always positive. That is not going to impact the sign of this function, whether it be positive or negative. Alright, so you're going to use the top. 1 minus x squared equals 0, because basically you can multiply through by the bottom because it's always positive. And then we factor it, 1 plus x times 1 minus x equals 0, and then we get x equals negative 1 and x equals 1 as our critical numbers here. And then if we find the y coordinates, we get the following: negative 1, comma, negative 0.5, and then the other one is going to be 1, comma, 0.5, plugging into the original function. Alright, so then the next part is going to be f prime of x. When you do f prime of x, it's ugly. So you do the bottom, excuse me, x squared plus 1 squared times the derivative of the top, which is negative 2x, minus the top, 1 minus x squared, times the derivative of the bottom, which you need the chain rule for. So it's times 2 times x squared plus 1 times the derivative of the inside, which is 2x, all over the bottom squared. So if you take x squared plus 1 squared and you square it, you get x squared plus 1 to the 4th. Simplifying that, what I would do is I'd factor out an x squared plus 1 on the top. If you don't simplify this by factoring out an x squared plus 1, this becomes the ugliest simplification known to man. So what I'm talking about is you have a factor in this first huge term of x squared plus 1. Also, you have a factor of x squared plus 1 in this second huge term. So you're going to pull that out front. So you say f prime of x equals x squared plus 1 times, well, if I pull an x squared plus 1 off that first huge term, I'm only left with one of them. So x squared plus 1 times negative 2x. If I pull an x squared plus 1 out of that second huge term, it disappears, right? It's gone. There is only one of them. There's only one factor of x squared plus 1 in that second term. So I'm left with 1 minus x squared times 2 times 2x. And then in the bottom, I have x squared plus 1 to the 4th power. Now, why is that important? Because now I can cancel this. It makes the top of this so much easier to simplify. Again, the bottom doesn't really matter when we end up finishing this. The bottom's always going to be positive. It's not going to impact the sign. Well, this is f double prime of x, kids, by the way. Meant to put f double prime. F double prime of x is equal to, now I'm going to simplify this, multiply through, So I get negative 2x times x squared plus 1. That gives me negative 2x cubed minus 2x. And then I have, this is negative, and I've got a 2, and I've got a 2x. So 2 times 2x is 4x, and then I'm going to put the negative on there too. So here's what I'll do. Before distributing through, I'm going to change this to a positive. I'll put the negative on the 2 that's here, but then I'm going to just make this whole thing into negative 4x. And then I'll distribute it through. When I distribute negative 4x through, 1 minus x squared, negative 4x times 1 gives me minus 4x. Negative 4x times negative x squared gives me plus 4x to the third. And that's all over x squared plus 1 to the third. Ugly algebra here, kids, but really, it's just algebra. Just have to be meticulous. That's the thing about algebra. It's not really about difficulty. It's just about being meticulous. And a lot of you don't like to be meticulous. That's the problem. Most people in the world don't like to be meticulous. So 4x cubed minus 2x cubed, that's going to be our first term, 2x cubed. And then negative 2x minus 4x gives me minus 6x all over x squared plus 1 to the third power. Now, what's the next step? Well, I'm going to take that and I'm going to set it equal to 0. Right? And I'm going to solve for x. So again, the bottom isn't going to matter when I set it equal to 0. Since that's positive always, I can multiply through by it. And I get 2x cubed minus 6x equals 0. I'll factor out a 2x, so I get 2x times x squared minus 3 equals 0. And then out of that, I'm going to get the following. X equals 0, x squared equals 3, so x equals negative radical 3, and x equals positive radical 3. Okay, so once I have those, I will go ahead and plug them into my calculator to get the actual points. So the actual points here, 0, 0. Negative radical 3 is negative 1.7, so I'm going to use that. Negative 1.7 and negative 0.4 when we plug that into the original function f of x. And then finally, radical 3 is positive 1.7 and positive 0.4. People have an awful time with the algebra associated with this. They don't have such an awful time with the calculus. It's the algebra. Now I'm going to go ahead and do my number lines and include those on there. So here is my f prime number line. It's only got 2 critical numbers on it, one at negative 1 and one at 1. And then my f double prime number line has possible inflection points at negative 1.7, at 0, and at 1.7. Okay, so remember, these have to be in the right places relative to each other. Alright, so let's check out the f prime number line first. Here's the most factored form of f prime. So if I look at that, I put in, say, negative 5. If I put a negative 5 into the first factor, I get a negative. If I put a negative 5 into the second factor, I get a If I put a negative 5 into the first factor, I get a negative. If I put a negative 5 in the second factor, I get 1 minus negative 5, which is a positive. So a negative times a positive gives me a negative over here. And then between negative 1 and 1, pick 0. If I put a 0 in here, I get 1. If I put a 0 in here, I get 1. So 1 times 1 gives me a positive number. And then if I pick a number over here, say 5, 1 plus 5, that's positive. 1 minus 5, that's negative. So positive times a negative gives me a negative. You've got to be very careful when you plug those into those factors. Remember, when you subtract a negative, you get a positive. Okay, so this goes from decreasing to increasing, so you have a bottom there, or a minimum. And then this goes from increasing to decreasing, so you have a maximum there. All right, so now let's look at the inflection points. The most factored form of f double prime of x would be right here, I would say. So use that pick something to the left of negative 1.7, say negative 100. If I stick a negative 100 in here, I get a negative. If I stick a negative 100 in here, when I square it, it becomes positive. So a negative times a positive gives me a negative over here. So that means it's concave down there. Okay, and then between negative 1.7 and 0, I had pick negative 1. If I stick a negative 1 in here, I get a negative. If I stick a negative 1 in here, I get a negative. Negative times a negative gives me a positive. Same thing with a 1. Put a 1 in here, I get a positive. If I put a 1 in here, I get a negative, so that turns out negative. And then finally, if I put 100 in here, I get a positive. If I put 100 in here, I get a positive. 2 positives gives me a positive. So negative means concave down, positive means concave up, right, on the F double prime graph. So you do have an inflection point here, you have an inflection point here, and you have an inflection point here, because it changes from concave down to concave up. I think I forgot to mention the concave down, concave up thing up above. So now all we have to do is use that information to draw our graph, put our points on our graph, and we will be done. So my graph has, first of all, a horizontal asymptote at y equals 0. So let me get a little eraser here and I'll make it dotted. Now you're not going to make it dotted close to 0, because close to 0 is not where horizontal asymptotes matter. It's as you go out towards negative and positive infinity that horizontal asymptotes actually take effect. Okay, so I'll just make it dotted out in that positive and negative x direction. Here's x, here's y. I'm going to make my graph red on this one. Okay, so what have I got? Well, I've got negative radical 3 and negative 0.4, so I'll put that, say, about here. Oops, I got to put it underneath my one here. So negative radical 3 is negative 1.7. You can write it like that if you'd like. I don't like where I keep putting it, so I'm going to put it down a little further. Okay, so negative radical 3, negative 0.4, and then negative 1 and negative 0.5, so negative 1 was here on my graph up there, so, and negative 0.5, okay. And then 0, 0, and then 1 and 0.5, and then radical 3 and 0.4. Now the concave up, concave down really comes into effect here. Here's the thing. This is your only minimum, right, from your F prime graph. This is your only maximum. So your graph will never change signs except for at those points. All right, so they have to connect to the other points. So obviously you're going to go here, and then you have to go through 0. I don't like the way that turned out, so I'm going to try to fix it just a tad. Alright, pretty shaky, but this should look sort of like it's concave down. This should look pretty much like it's concave up. Okay, now once I have those, because it is, see, this is concave down, negative, this is concave up. You have a min here from your F prime, you have a max here from your F prime graph. Finally, you're concave down. Now, after 1.7 or radical 3, your graph becomes concave up again. And because this is a horizontal asymptote, it has to get closer and closer. Well, the only way to get closer and closer to this is to become concave up. Because if you remain concave down, you're going to have to cross, right? You don't want to cross. You're not going to cross as you approach infinity. You're going to become concave up at this point and stay concave up and just get closer and closer to that graph as you go towards infinity. Here, this is concave up, it needs to become concave down so it gets closer and closer to that graph as you approach infinity. And that's why those are both inflection points. Okay, so on this one I'm just going to, your inflection points, instead of labeling them on the graph, well, I can label them on the graph. That's the easiest thing to do, I guess. Okay. Technical difficulties. There we go. Alright, so let's label all our graphs, our inflection points and our critical points. Oh, I forgot to label 0, 0 on my graph. Okay, so this is an inflection point because you change from concave down to concave up. This is, and this is. This is a critical point at -1, -0.5. Not only is that a critical point, it's an absolute min. There are no points on the graph that are going lower than -0.5. And this is an absolute max. There are no points on the graph that go higher than 0.5. So that's it, kids. That is this graph. I would throw a label on it. F of x is equal to x over x squared plus 1. The last problem on your homework is like this. It's a tough one. I need you to take the time to do it. I have posted all the answers online, so hopefully you'll be able to do this well. And good luck with that. Okay, so again, to review, the homework due Thursday is the worksheet, numbers 1 through 5. The homework due Monday, the 23rd, is this, and on the 23rd, we're going to take time to go over all this graphing stuff, and then you will have a quiz on Wednesday, the 25th. So I will be there to go over some things with you on the 23rd before you take your big quiz on the 25th. All right, folks, so have a wonderful day, and you will have no more lectures coming from me. The next time you hear my voice, it will be in person. Have a great day.